Hey guys, my name's Tyler. I work here in town at DataStax. I'm a Cassandra engineer. Actually, I just got voted in as a committer today, which is nice. And I also work on the drivers, mostly the Python drivers. So I guess before I get started, thanks to Aaron for having me out. Definitely excited to talk to all you guys. And I'll be giving about 3/4 of this talk, and then I'm going to turn it over to Joaquin, who also works with me, just to show a couple of cool ways to integrate Cassandra with Django that he's been playing around with. So how many of you guys are actually like running Cassandra in production? Are any of you guys doing that yet? No, okay, I didn't expect so. How many of y'all know a fair amount about Cassandra? One person. Perfect. Okay, so I kind of assumed that would be the case, so I started out at a pretty low level here with Cassandra. So I'll cover a lot of introductory details. So Cassandra was first started at Facebook. They open sourced it about 5 years ago. And most of the early users were kind of hip web companies. Jig was a big early user. Reddit has been running on Cassandra for a long time. And then about 4 years ago, DataStax started, and we've been the commercial company behind Cassandra since then. We've been doing most of the development on Cassandra, but a lot of the contributions still come from the community, especially from companies like Netflix, who are huge users of Cassandra. They migrated their entire infrastructure away from Oracle to Cassandra at the same time that they moved from a physical data center into Amazon AWS. And since then, there've been a lot of new users of Cassandra. It's really expanded into many different segments. Got a lot of telecom companies, financial companies, government agencies. The list goes on and on. It's definitely not a niche product at this point, or a niche technology. It's got a wide variety of use cases where it can do some very good things. Cassandra is, like all tools, it's really good at some things, and it also has its weaknesses. I won't say that it's a perfect database for every use case at this point. We're certainly working to expand the points where it's weak right now, but it definitely has its strengths. So I'm going to talk a little bit about kind of scenarios where you would use Cassandra. I'm going to use a few big users of Cassandra as examples of kind of those nice features. So one big user of Cassandra now is eBay, and they use it for a few different patterns, but one of the main use cases they have is time series data. And you'll see this again and again in Cassandra usage. Time series data is basically anything where you want to end up doing something like select star where dates falls in this range, or give me the latest 100 events that happened. Anything where you're working with dates, you're interested in sorting things by time, something like that. So eBay also uses Cassandra. A big part of the reason is it's multi-data center support. It's very much, I think, best in class in terms of the way that it behaves in a multi-data center environment. You get a lot of flexibility in how you handle, say, failures of an entire data center, or how you want, if you want to wait for synchronous replication across data centers or do something more asynchronous. You have a lot of good options there. And that's definitely a big reason why eBay is using Cassandra. And of course, it doesn't have to be the cloud. Works just fine on physical hardware. But certainly a lot of Cassandra users do use it in Amazon EC2 in particular. So it's pretty well tuned for running in that environment. Another reason that eBay uses Cassandra is it has support for distributed counters. So distributed counters are actually something that's very difficult. There are a lot of different implementations of distributed counters, and they all sort of have their sets of trade-offs. Cassandra's original implementation does have some flaws. We just improved it for Cassandra 2.1, which is currently in beta. But if you're looking to count things at a very, very high throughput over, say, millions of different counters, this is one thing that Cassandra kind of does that it's hard to find anywhere else. Twitter also is a heavy user of the distributed counters. And then Hadoop support. So if you want to run MapReduce jobs to do some large analytics on your data, it's important that that be fairly painless and that you also don't impact your production cluster, right? So Cassandra's kind of built-in replication makes it very easy to run a MapReduce job against some of the data in your Cassandra cluster without having any extra ETL steps, and also without impacting the clusters that are serving your production application. Adobe is also another big user of Cassandra. You'll see a few of the reasons repeated here, but low latency. This is something that Cassandra's definitely known for. It's much better at doing lots of small, low latency queries than it is, huge complex queries. It basically doesn't do big complex queries at all. So you can get things like a 95th percentile read latency of half a millisecond, and this is at the scale of somebody like Adobe. Scalability is another thing that Cassandra is excellent at. So basically, when you want to grow your cluster, you basically just start up a new Cassandra node, and all the other nodes automatically know what data it's supposed to own. So they'll do that quick calculation and then just stream data to the new node. And it's kind of magically in the cluster. It's not a difficult operation at all. And the nice thing about the way that Cassandra scales is that it scales linearly, both in read performance and in write performance. So with most master-slave systems, it's fairly easy to scale reads because you can just add slaves, right? Writes tend to be more difficult to scale in those cases because the master is a bottleneck in that case. But with Cassandra, if you double the number of nodes, you get basically exactly twice the throughput in terms of reads, writes, and storage capacity. So it's extremely linearly scalable, up to at least 1,000 nodes. That's about as large as we've tested. And tunable consistency, which I'll cover a little bit later. Instagram has also been a really big user of Cassandra lately. Mostly just for the efficiency and high availability are the key points. So one of the reasons why it's extremely, Cassandra has extremely efficient writes and can get very good throughput on writes is that when you do a write, basically it just has to do two things. One is to append the write to a commit log. So commit log is just, it's like a transaction log or a write-ahead log in other databases. It's just appending to a file. So the disk doesn't have to do any seeks. Even on SSDs, you don't have to worry about write amplification. It's just doing nice appends. That's about as cheap as it gets to write to a disk. And then it updates an in-memory data structure. And when you pile up enough of these writes, it eventually flushes it out to a large immutable file called an SS table. And then from there on, almost all of the on-disk operations just involve large amounts of sequential I/O. So it's very efficient in terms of how it uses the disk. And so far, Instagram has 6 nines of availability on Cassandra. So some of the things that we really focus on when we're working on Cassandra, scalability, as I mentioned, we want all the operations to scale linearly so that you can just sort of, if you have a performance problem, you can always add nodes, and that kind of always works. It's nice to have that as an option. High performance, obviously. Ease of use is something that Cassandra's kind of had a weakness in, but it's something that we're focusing on a lot. So it does have a reputation to be a little bit difficult to get started with. Most of that has to do with changing the way you think about storing your data, but we're trying to make that a little bit easier, so we've been focusing on that a lot. And of course, reliability and availability. Some quick benchmarks. This is by somebody at the University of Toronto. It's just kind of demonstrating the linear scalability I was talking about. This is a mixed read, write, scan workload. You can basically see as the number of nodes goes up, performance goes up linearly. This is a second benchmark by some other company that I'm not that familiar with. It basically shows the same thing. The x-axis is logarithmic there, though, so that's why it looks like a exponential growth instead of a straight line. And ease of use, this is one of the things that changed. It's kind of been a work in progress for a couple of years now for Cassandra, is using a query language instead of the original API that Cassandra had. And the query language does resemble SQL quite a bit. It's almost a subset of SQL. So I'll show you a little bit more about how it works in a bit. And these are just some nice quotes from Twitter about Cassandra's resilience to failure. Those include things like tolerating the failure of an entire data center with no downtime. Here's a scenario that's in your classical master-slave architecture tends to cause problems, right? So the normal way that you're sort of scaling your database would be to have some kind of partitioning scheme. You're routing all of your operations through that. It's selecting which shard or partition of your data you need to operate on. And then you have a kind of a master-slave setup within there, right? So writes go to the master, replicates to the slaves. But master-slave systems handle failures usually with failover. And failover tends to have some serious problems. Even in fairly mature products, there are still corner cases that require manual intervention, or it can take a long time for failover to work correctly. This is just a bit from a slide by Armin Ronker, the author of Flask. So I don't know exactly what happened to him here, but just kind of a typical example of what can happen. And there are many, this is actually a much more common problem than people tend to think. That the bottom link there just shows some recent research on sort of how frequent network partitions are and what the failure scenarios were like. So Cassandra has a different architecture. It's not master-slave. It's more like a peer-to-peer system. So there are no special nodes in the cluster, and that's one of the ways that it gets such good availability. So basically, instead of having sort of that routing layer from the previous slide, any node in a Cassandra cluster can figure out where the data is supposed to live. So your client can contact any node in the Cassandra cluster to perform a query. And that node will do the calculation and route it to the correct replicas. So you can sort of tolerate, in a sense, the failure of any arbitrary node without any problems. So the way that it splits up the data and does this calculation, it basically depends on the primary key for the data, or more technically the partition key. So whenever a read or a write comes in for a row, it looks at the primary key and it runs it through a hash. We use murmur3 hash because it's fast, but MD5 works as well. So this gives you a 64-bit number. And basically, each node in the cluster owns some portion of that, a range of that space for all of the possible 64-bit numbers. So I've got an example here. So say you're inserting a row where the primary key is Jim, just the string Jim. It hashes to something, I don't remember, hashes to 5e, so on and so forth. But node C owns the range from 4 whatever to 8 whatever. So 5e falls in between that, and basically node C is the replica for that piece of data. It uses a scheme called consistent hashing, which some of you may have heard of. But every row, you determine the replicas for it in this exact same way. A few more examples on here. So you normally don't just have one replica. You usually want multiple replicas for availability and durability purposes. So the kind of simple method for doing that is if we calculate node C as being the replica for a piece of data, we'll kind of just go to the next node with the higher number and say that it's the second replica, and then continue on to say the third replica if we want a replication factor of 3. So with a setup like this, any of those 3 nodes can go down, and you'll still be able to read or write any of that data, depending on a parameter that you specify with your query, if you want to be able to tolerate that. And to make the picture a little more confusing, it's not actually split up into these huge ranges anymore. They use much smaller slices, which are called virtual nodes. It just makes it a little bit easier for maintenance operations. So we'll walk through an example of what happens with a read request, and specifically what happens in the failure case. So on a normal read, the client, which is just your application, sends in a read request, right? Say it's asking for a row where the primary key is Joe. The coordinator node here can be any member of the Cassandra cluster, and it will run that hash on Joe. From the hash, it does that ring calculation that I just showed, and it figures out that these 3 nodes are the proper replicas for that piece of data. So then it looks in it, sees that this node in the middle has been responding most quickly, so it chooses it to forward the request to. And that node actually goes on disk, reads the data, and returns it to the coordinator. The coordinator sends it back to the client. So there's a parameter that you can specify with queries called a consistency level. And what the consistency level says is basically how many of the replicas have to respond to consider the operation a success. So this really controls kind of your trade-off between availability and consistency, right? So if you know that you have 3 replicas, you could say anywhere from one of them needs to respond to all 3. If you say that you want all 3 to respond, obviously they're all going to have consistent data stored, but you can't tolerate the failure of any 3 of those nodes, right? And likewise, if you say that you only need a response from 1, you can tolerate the failure of 2 of the 3 nodes, but you don't have as strong of a consistency guarantee. One of your replicas may have newer data than the others. So if you do another read at consistency level 1, meaning you only need a response from 1 replica, you might read stale data under failure conditions. So if we use a consistency level, and this is common, called quorum, where you ask for a majority of the replicas to respond, then the coordinator will send out the request to 2 of the 3 replicas. It will get back the results from both of those, and then it will look to see which of the data is newer, and it will return that to the client. And if necessary, it will repair the replica that was sort of out of sync or had stale data. So the nice thing about quorum, and the reason why it's pretty common, is obviously you can tolerate the failure of one of these 3 nodes with no downtime, but since you're writing to guarantee 2 of the 3, and you're reading from 2 of the 3, there's guaranteed to be overlap of 1 replica. So you get a guarantee that you're always going to read the most recently written data. So you still have pretty good consistency guarantees. There's strong consistency, but you also have some amount of flexibility in how you can handle the failure of some nodes. So there's a variety of consistency levels. The ones I just talked about, one, quorum, and all, are typical. In multi-data center environments, there's a couple of special ones. Local quorum just waits for a quorum of the replicas in your local data center, and each quorum waits for a quorum of basically each of the data centers. So in a multi-data center environment, you can say, I want to wait for a quorum of the replicas that are in my local data center to respond, but I don't want to wait for the remote data center to respond, because obviously latency is going to be extremely high there. So you can sort of get locally strong consistency, and you're still replicating to the remote data center, but you're not paying the latency penalty to wait for replication to the remote data center. So Cassandra has extremely, well, let me just talk about this use case first. So common pattern, you're creating users, right? Can you guys all see that? Hopefully so. So say we have one client. It wants to create a new user, P. McFadden. So it runs a select, sees that the user doesn't exist, and it decides it's going to go ahead and create the user. At the same time, a second client starts doing the same thing, also sees that the user doesn't yet exist. And so you wind up with both of them inserting the user. The last write wins, it gets overwritten. Cassandra can't distinguish between, basically insert and update are the same thing in Cassandra. It doesn't do reads before write. So there's no sort of inserts. Well, normally it doesn't do reads before writes. So it's not verifying that the data doesn't exist whenever you're inserting here. So recently, Cassandra added something that we're calling lightweight transactions. And what this adds is a little bit of syntax to do something like if not exists. And remember, this isn't a distributed database with multiple replicas. So it's not just a simple kind of local transaction. It actually is a little bit more complex than that. But it's basically just allows you to do if not exists. And if it does happen to exist, it'll be nice and return the row that you expected to not exist, just because that's a frequent behavior anyways. So the way that it does these lightweight transactions is through an algorithm called Paxos, which is a distributed consensus algorithm. It's quorum-based, so you still have some tolerance of failure of replicas. All you have to have is a quorum of the replicas for the data you're performing a transaction on, for the transaction to work. And if you're interested in Paxos, or you don't know about it, it's pretty cool stuff. Just check out a paper called Paxos Made Simple. The downside of this, since it's running this whole consensus business before it's actually mutating the data, it's a lot more expensive. So you really want to only use this for a very small portion of your operations, right? You shouldn't be doing this for every operation. It's only for cases like that, that user creation where you really need some level of transactions, and there's not a good way to do it with just normal eventual consistency. But by and large, you should expect to work with eventual consistency when you're using Cassandra, and it's not as scary of a thing as a lot of people think at first. There's a really good post by Christos, I think he's at Netflix, and he's just talking about sort of the implications of eventual consistency and how to reason about using it in a real environment. So that's my super quick introduction to Cassandra. Like none of y'all knew anything about it as far as I could tell. So that's probably a lot of stuff. So do you guys have any questions so far? Yes?
So how does the client know which node to talk to? You said it could talk to any node. What, does it have a list of nodes? Like what if the node it's trying to talk to goes down?
Yeah, so the clients usually, and I'll talk about how the Python driver does this specifically, but the clients normally maintain connections to several nodes in the cluster, sometimes all, if the cluster is small. So they're built to handle failure of some of the nodes as well, and most of them do a transparent retry on failed operations against another node. So the drivers tend to be a little bit more complex than your typical database driver as well, in that they're a lot more fault tolerant. They've got sort of built-in retry mechanisms. But yeah, the driver doesn't need to talk to any specific node at all. And so typically they'll just sort of round robin through a list of nodes to just spread out the operations around the cluster.
So when you add a node, how does that propagate to the drivers?
So when you add a node, there's a few ways that it propagates. One is that the driver will basically register for notifications from the cluster about changes to it. So if a node leaves or a new node is added, that information will get pushed to the driver so it can update its set of connections or open new ones if needed. And the other is that there's a system table that just lists all of the nodes in the cluster, and so periodically the driver will consult that as well to see if that's changed.
Where does that system table live? Is that a single node or all nodes?
That's on all of them, but it's not replicated, so it's sort of local to every node in the cluster. If that makes sense. Yes?
So when you add a node then to the cluster, how does your hashing algorithm would basically address a certain node? When you add one, how does that affect that table, and then how do they get moved over, or what happens in that process?
Sure. So whenever you're adding a node, let's see if I'll go back to it. That's really far back. I shouldn't have done that. So when you add a node, it basically it picks its position in that space of the hash range, right? And it announces that. So the rest of the nodes see that it's going to start living there. And what they start doing is they begin by forwarding write requests to that node. So any writes that it sort of should own once it's fully part of the cluster, it'll start getting immediately. But those don't count towards the consistency level. They're just sort of an extra write. Once it's so after that starts forwarding the writes, all of the nodes can look through their data, see what of their data falls within that token range or that hash range, and then they'll just stream those chunks of data to that node. And once that streaming process is complete, that new node becomes an actual owner for that range, that hash range, and whatever nodes used to own that portion but sort of got pushed out by the new node, they no longer get writes forwarded to them for that range. And then it's a manual operation, but you just tell those nodes to clean up data that they no longer own. And I forgot to mention, but reads also start once it becomes sort of an official member and after the data is streamed. So the client doesn't need to know any of this, but the node that's acting as the coordinator does care about this. So it's sort of transparent to the application, but obviously it's not transparent to Cassandra itself. Yes?
You saying if it doesn't own the information anymore, then how, if you take it out, that node out, then how is it stored in all the other nodes?
Sure. So I don't want to go through like 1,000 slides again to find it, but so remember that I mentioned that you typically have a replication factor of 3. That's pretty common. So every piece of data is stored across 3 nodes. So say you have a hardware failure on one of those 3 replicas. What you'll do is you'll basically run an operation that lets the cluster know that this node's down and it's not coming back, and that it needs to basically repair the data. So you only have two or three replicas at this point. So those two replicas will stream data to a third node in order to have a third replica there. So basically, you're taking the dead node out of that kind of hash ring, and whatever other nodes happen to be its neighbors there, they become the new owners for it. It's a pretty simple process as well. All it is just looking through the data to see what falls within that range that the node owned and streaming it to a new replica, and then that replica becomes another, once the streaming is complete, it's just treated as another normal replica.
That's just assuming you have more nodes.
Yeah, so if you only have a replication factor of 1, right, and you lose a node, the data is gone.
1 or 2, then. Because if you have 2 nodes, it's just complete replicas of each other?
Sort of. So when I say replication factor, all that I mean is that there's that many copies of every row in the cluster on different nodes. So replication factor 3 means that there are 3 distinct copies on different nodes. So yeah, durability is a concern there. That's part of the reason why you don't want to use replication factor of 1, right? If you've only got 1 copy of your piece of data. You should also back up your data as well, right? Just like any other database backups report.
What's the transfer rate of the assimilation of a new node? How long does it take?
So it depends a lot on the size of your nodes. Some people run nodes with run them quite small, let's say like 50 gigabytes each. Other people really push it and do multiple terabytes per node. So Cassandra can handle multiple terabytes per node, but it's operations like this where it kind of bites you a little bit. It takes a while to stream a terabyte of data. So by default, Cassandra throttles the streaming because you don't, whenever you're adding a node to the cluster, you don't want to put too much strain on the existing nodes, right? So it throttles it to, I don't even remember, it's something like 15 megabits per second of outbound streaming per node. That's pretty much dictates how long it will take. Yes?
So like what is the typical node, like how many nodes do you typically have, like a small, medium, or large scale
Sure.
system?
So the number of nodes you'll have in your cluster, usually the minimum is 3. And the reason is that allows you to use a replication factor of 3 and do quorum consistency level reads and writes. That's a very common thing. Usually you don't see anybody running a production cluster with less than 3 nodes. We have customers that are running just shy of 1,000 nodes. So that's about that's the high end of the scale right now. Most of our Cassandra users and our customers are running probably more in the 8 to 30 range. That's sort of what suits most businesses. For the large part, how many nodes you need depends on what kind of read throughput you need. As I talked about briefly, writes are extremely cheap in Cassandra. Reads are a little bit more expensive because they can involve some random I/O on the disk. So you do tend to optimize for reads, but reads are kind of your limiting factor in Cassandra, and those tend to dictate how many nodes you need. Does that answer your question?
Yeah, definitely.
Cool. Yes?
Do people tend to use like a consistent number of nodes, or is this the kind of thing where you add more nodes when when you're getting really hammered by requests or something?
Yeah, so you're talking about sort of like an elastic scaling situation. I think there have been a few people that have kind of tried that. It is a little bit easier now. I talked about virtual nodes for just a second there, where it's instead of being a huge, big contiguous range for each node, they're split up into little chunks. That does make it easier to pull out nodes and add nodes to the cluster. So it's a little more feasible today, but the cost of the streaming usually makes that not worthwhile to do on like a day-to-day basis. It does make sense to do something like that, perhaps, say, when it's going to be Black Friday soon. We had a lot of our customers do that. That's certainly nice. A lot of them in particular, they'll run on physical hardware for the most part. And when something comes around like Black Friday, they'll use EC2 to grow the cluster. So that's a pretty nice pattern for scaling your cluster. But yeah, day to day, you won't see the cluster size change all that much. Yes?
Is it bound by anything? Like, like Redis is all memory for the most part and everything. So like, is this all on disk? You all terabytes of the disk and reads from that, or?
So it does have several layers of caching. Cassandra's written in Java, so it's running on the JVM. The JVM currently with the garbage collection technology on the JVM, about the largest useful heap size you can have is 8 gigs. So Cassandra, it's sort of, that's one of its main limitations is the heap size. But for the past couple of years, we've been moving most of Cassandra's in-memory structures off the heap. There's actually ways that you can get around storing things on the heap. So that avoids the garbage collector, and so that's becoming less of a limitation. As I mentioned, the size of how big you can push a single node, it has to do more with how many reads per second you want to support and how efficient those reads are, and also if you can tolerate the pain of very large maintenance operations, like replacing a node that has 5 terabytes. Yes?
Do you have a limit on the number of nodes like Mongo does, or?
There's no limit on the number of nodes. It's, some of the tools start to become less useful in the high hundreds. You're certainly a little bit adventurous once you get to that point. But everything, there have been a few bugs that we've had to fix for things to work at that scale, but with those resolved, it really does scale linearly, at least up to about 1,000 nodes. Presumably more, but nobody's really tested that yet. So, yes.
What is Cassandra not good at?
What is Cassandra not good at? So primarily, so I mentioned it doesn't have capabilities for very complex queries. So you can't just sort of run any arbitrary SQL query and expect it to eventually return a result. The API is much more limited than that. You basically have to make queries that ask for a very specific piece of data. And I'll show you a little bit about that in a bit. But if you want to say just do some kind of more analytical query or exploratory analysis of your data, that's going to be a pain in Cassandra. So Cassandra is much better at if you know exactly what kind of problem you're trying to solve and you want to solve it very efficiently, that's where Cassandra is a good fit. If you don't know that yet, and you're just trying to play around with the data, or you want to have a lot of flexibility in terms of how you query the data, that's where Cassandra is not going to be great. Transactions, the lightweight transactions that I mentioned are sort of the limit of Cassandra's transactional capabilities. If for whatever reason you need more sophisticated transactions than that, usually you don't need them as much as you would think. People are just so used to using transactions that they're not aware of other patterns that you can use. But that is something where if you have highly transactional operations, that's something you're going to have to do a lot more work for with Cassandra. Yes?
Is Cassandra just a backend database, or does it integrate with other frameworks or content management systems to create user interfaces?
Not exactly sure how to answer that. I mean, the project itself only includes the database. It kind of ends at the query language. That's kind of the most high-level API that the project itself presents. The drivers usually kind of extend that a little bit more. People like to try and integrate it with things like, I'm forgetting all my Java framework names now, but yeah, JBoss or JDBC, JPA, all that kind of stuff. The thing is that a lot of frameworks and tools are designed with relational databases in mind, and it's just barely enough different in Cassandra that they really can't handle that difference. So you won't be able to just plug it into a lot of frameworks and go. I'll be showing a little bit about how you can use Cassandra from within Django, but it's not using the built-in ORM. It's hand-coded. And to an extent, the reason why ORMs don't work in Cassandra is that kind of instead of modeling your data or your objects, you're instead modeling your queries. You're kind of, in a sense, pre-building the answers for the queries that you care about. So that's what I kind of meant when I was saying if you know exactly what you need to do, it can do that very efficiently. It allows you to build those answers in a very efficient way, but you still kind of have to know what the queries are. So that's why an object relational mapper doesn't tend to work as well. It's not really relations. You care more about queries than objects in Cassandra. Does that answer your question?
Yeah, I think so. That's interesting that it favors queries over relationships.
Yeah, that's something that gives people the most trouble when they're getting started is thinking about their data model. And you really do have to say, model your queries, not your objects, not your data, not your relations. It's all about the queries that you want to run.
Also, if you think about your business cases, I mean, if you think about Netflix, it's not like they're doing really complicated things.
Right.
It's, here's a video, you stream it, you vote on it, and, that's about it.
Yeah.
Probably, if Facebook is using it as a backend, that would probably be a far more complicated.
Yeah, so Facebook originally built it for inbox search, which actually is a pretty simple thing. You're right, Cassandra tends to get used for kind of simpler operations, but ones that you want to do tens of thousands of times per second, or you want to support a huge number of them. Netflix has something crazy like 70 different Cassandra clusters, so they do a ton of different stuff with it, but every operation that they do is kind of simple on its own. Any other questions? Not yet. Okay, so this is probably a good time for a quick break. After this, I'm going to talk a little bit about the Python driver for Cassandra. I wrote that as well. And then I've got a quick example of a project called Twissandra. That's a Twitter clone that uses Cassandra as a backend. This will show you a little bit about kind of how you model your data for queries. And then Joaquin's going to be talking about Django session storage with Cassandra after that. So however long, like 5-10 minute break, and then we'll get started again.
5 minutes.
Thanks.
First, like 45 minutes, so I like just both got started. Oh. Yeah, it was good. But I just didn't think about No, Peter had it at his office. I actually worked with both. I'll probably no, not yet. So I'm just going I think Joseph.
Do you know all the seats up front we're taking?
Yeah, so they still.
I work for myself. At the moment, writing a Django book. I'm technically a freelance consultant in Python and Django. And sometime in the last 6 months, so I started teaching Django last year. And then I ended up currently writing a book for Addison. I'm a huge fan. I bought it. You know, you're a startup, you don't know what you're doing, you want to just get something really quick and dirty. And, you know, you seem Right. You could have figured that out after you were true. So, I was doing a lot of consulting for startups, and the number of times I consulted for a startup that didn't take bad advice and needs the right. Build quickly and dirty until you know exactly what you're building. Like, if you don't know exactly what you're building, if you haven't had time to use your text or to monitor text, then you should be going straight to you should be doing a really quick and dirty text in Drupal in an afternoon. Show up the next morning, find other people, see what you as opposed to 2 weeks in Django and then going. So what is I have no yeah, cool. Maybe that's a number I got from 2008.
I'm sorry. That's what
Yes.
Yes. So is there just some sort of security?
No, that's fine.
Yeah, just security.
Sitting awkwardly listening to the conversation.
Absorbing knowledge. John. Just got a John.
Not a fan of Java.
It's actually fine. It's not bad. It's good for a lot of things. It's got strengths. I think it's a bad rap. Different styles. Probably. A lot of people hate it, but I don't know. I think it's a lot of.
What was your like? We're not working.
It's not great. It's really doesn't do it. It's like Cassandra has limitations. So it's just
For me, it's just like your first like makes sense for me as a person. Which is overrated. Most of the your high school your network gets more important.
yeah, it's kind of what I was considering switching to dynamic people, like this kind of setting type of kind of security services like contracts and form. So I don't know. This thing on that is going to be. I guess you like.
All right, I'm going to get started. So in this second half, like I mentioned, I'm going to talk a little bit about the Python driver. I think the API is pretty simple, so it shouldn't involve a lot of explaining. And then I'll talk about Twissandra again, like I mentioned, the Twitter kind of clone. I just rewrote it today to use the new Python driver instead of the old one that I used to maintain. It's like half done, so no live demos, fortunately for me. But after that, Joaquin's going to show the session storage for Django. So the Python driver, you can check it out on GitHub. DataStax Python driver. That's Apache licensed. If you want to install it with pip, it's just called Cassandra driver. I've been working on it for about 7 or 8 months, half time basically. So it's a pretty complex piece of machinery just because it does have to deal with the distributed cluster. But like I mentioned, hopefully the API is pretty nice and it should look, for the most part, pretty familiar. So just opening a connection to Cassandra, basically you pass in a list of contact points, just a few nodes in the cluster. It'll open some connections to those, figure out what the rest of the nodes in the cluster are, and then it'll automatically connect to those as well. And then you create a session which operates on a key space usually. A key space, it's like a database. It's just a group of tables. And that's sort of where you define your replication settings for your data. And I already said that. So the query interface, it should look really familiar. I used CycloPG2 is one of my main references when working on this. So there's a lot of similarities there. Yeah, you just run execute, you get back rows. By default, the rows come back in a named tuple. So if you're not familiar with that data structure, it's pretty handy. It's like a tuple, it uses about the same amount of space, but you can access things by the field name here, like username and ID. So this is just treating it like a tuple instead. You can also just have it return a dictionary or an ordered dictionary or some other structure if you'd like. just in terms of providing parameters, should look very familiar again. All you do is use placeholders, %s, or you can do the named style placeholders. This is exactly the same as this PG2 here as well. And it automatically does all the escaping. You don't get SQL injection. And injection is still a problem here as well. There's fewer things you can do with it typically, but it's a query language, so you have to worry about escaping things. So prepared statements. Prepared statements are just a way to send a query to Cassandra. It parses it once. It gives you back an ID. And then you can, whenever you're executing that query, you just pass that ID and the parameters that you want to bind for that query. So here we're selecting an account where ID equals some parameter. So after we prepare it, we'll just reuse it over and over again, and we just provide the ID. So it saves a lot of network bandwidth, I guess, and Cassandra doesn't have to reparse the query every time. So anytime you're executing queries multiple times, really, prepared statements are the way to go. So the driver, this is something where it's a little bit different from most database drivers, and including the older drivers for Cassandra, which none of you guys have used because none of you use Cassandra. But it has really good support for asynchronous queries. The reasons for this kind of has to do with how the driver uses connections. It actually can multiplex multiple operations over a single connection. So you can have multiple operations in flight at the same time with one connection. Cassandra can respond out of order. It basically allows the driver to more fully utilize a single connection, get a lot better throughput with a single connection. But it kind of requires that the implementation be somewhat event-driven. So really the driver performs best when you can use it in an asynchronous style. And it's got a couple of ways to do that. Probably the most simple way to do that is with kind of a future interface. You use futures in Java. This is like that. You run execute async. You get back a future. And anytime that you want the result, you just call future.result. If it was successful, it returns the rows. If it failed, it raises an exception at that point. So this is nice, especially, and I'll show some examples of this, I think. Yeah, I do. I'll just wait and show you those. Here we go. So if you want to run some queries concurrently, so you do have a couple options. Say we need to select or get the info for a bunch of users. We have a list of IDs. So one option is to run select star from accounts where ID in list of IDs. And that'll work just fine, but it's slightly, it has some trade-offs in Cassandra compared to the style that I'm using here. So when you do this giant in list, what basically happens is the coordinator gets this query, and it breaks down that query into sort of one query for each item in that in list. And then it fans out the query to the actual replicas for each of those rows and waits for all of them to respond, and then it responds to the client. So that puts a little bit of extra load on the coordinator. It has to wait for a lot more things. It's holding more things in memory. And if any of those operations fail, like say the replica for just one of those items in that big in list goes down, you have to retry the entire operation. The entire operation fails, you retry the entire thing. So it tends to perform worse under failure. So an alternative that tends to run a little more smoothly with Cassandra, and that happens to work really well with this asynchronous query execution, is to run a separate query for each item in that in list. You get your future, and you just queue up the futures. So you're letting these queries run concurrently. And then once you've submitted all of the queries, then you go through and wait for all of them to complete. So that's basically what's happening here. We're just building up a list of futures and calling .result on all of them at the end. So you do get quite good throughput with this method. And in the case of a failure, you only have to retry one small query instead of the entire huge query. So another way that the asynchronous queries can work is with callbacks. So any of you guys have used Twisted. This is a really lightweight, basic version of that. So you can just register a callback function, an airback function, and you can also pass extra arguments to that. So essentially, whenever the query completes, it'll automatically call your registered callback function with the results. So that can be useful for a few things. There are some limitations in the driver around that. You have to be a little bit careful about throttling your request, because you can kind of overload the driver. It's not too good at throttling a huge number of these requests if you use some crazy patterns. But it works pretty well for lightweight usage. And actually, it gets the best performance of any pattern with the driver, just because it keeps everything running on the thread that's running the event loop. So if you guys have worked with event-driven systems, you'll know that they're, at least in Python, they're all single-threaded. This kind of emulates that same pattern. In terms of legitimate support for event-driven systems, Twisted, G-Events, those are in the works. They should fit quite naturally. G-Event will probably be the first one. They're not there yet, but shortly we'll have some good support for those. Query tracing is something that Cassandra is awesome at now. So if you're having performance problems with a query, in Cassandra it's a distributed database, right? There's a lot of things that can go wrong, or that can be slowing down your query. So tracing is a great tool for figuring out exactly where the slowdown's happening. Basically, you just set a flag to say to trace the query. Cassandra internally does all this tracing. It stores the trace in a system table, and then the driver basically automatically pulls that data out when the query is complete, and you get a sort of an ordered list of here's what happened with the query, with timestamps, with millisecond resolution. It covers the coordinator node and the replica nodes, so it's pretty detailed. It's definitely a nice feature. It can help a lot with optimizing the queries. I don't think let's see here. Yeah, here's an example. So that's basically all you have to do is just set trace equals true. And it should print out pretty nicely. So I didn't make too many more slides on the driver, but just a few things I'll just mention real quick. Like I said, it does handle failure of queries transparently. So say if the coordinator node goes down, it can transparently retry the operation against a different coordinator node. And there's quite a few options for tuning exactly how it will handle those types of failures, how it will respond to different failure scenarios. But the defaults are pretty nice. It's also designed to work well in multi-data center environments. So you can tell it what data center is local, and it will only query nodes in the local data center unless, say, it thinks that they're all down. And in that case, it can resort to the remote data centers. I was just about to say something, and then I forgot. But it can also do it. It's got a few other nice features that probably you have to know a little bit more about Cassandra to know why they're important. But so far I'm pretty happy with how it's coming out. So any questions on the driver and how it works? Yes.
Well, you said you're currently making it work with Twisted and G-Event. Is that going to be sort of a loose open reactor model that somebody wanted to come along and make Tornado's IO loop work with it or something like that? They could?
Yeah. So I kind of designed it like that to kind of have a pluggable event loop. So right now it has a couple of implementations. One of them uses async core, which is a module in Python standard library, and the other uses libeb, which is a C library that is much more efficient. Not a lot more efficient actually, but Yeah, so basically adding G-event support, we'll do something similar. That'll probably be a little more invasive, so that'll kind of break the API apart a little bit more. Once we get the first major change in like that, then it should be a little more clear how to add support for something like Tornado. But yeah, it's definitely kind of designed to be a pluggable system there. That did remind me of a couple things I wanted to mention. One is that doesn't support Python 3 yet. Actually, just started working with a guy yesterday on getting support for that. So if any of you guys use Python 3, should be supported soon. The other is that it does run pure Python, or can run pure Python, which means it works on PyPy and on Jython. The nice thing about PyPy is that it has crazy good performance with the driver. I've done some benchmarks, and it gets 2 or 3 times the throughput of CPython, which I was pretty impressed with. I'd done some benchmarks way back in the day, and they weren't quite that good, but it's getting pretty fast now. So if you really care about throughputs, PyPy's pretty sweet combination with the driver. Any other questions? No. Okay, cool. I'm going to move on to Twissandra real quick. So this is also on GitHub. I just started a branch today. So this was using the kind of the old school Python driver that I used to maintain. I just started switching it over to the new one. And that's on the SQL 3 branch. SQL is the name of the query language. I don't think I mentioned that. It's just Cassandra query language. So, like I mentioned, the data model is usually the trickiest part to get right. So going through a few examples of what you would do can be helpful. So say we want to just model the followers of a user, and our only real query is going to be give me the followers of a user. We've got something that should look pretty familiar. Create table statement. It's keyed by the user. Got a column for the followers, and just a timestamp. And the most important thing here is the primary key definition. So the first part of the primary key is the username, and that's what Cassandra is going to partition by. So if you remember back to where I was talking about all that hashing business, and I said that it worked on the primary key, I said technically it's the partition key. This is what I meant. The first part of the primary key is the partition key. That's sort of how it decides to split up the data around the cluster. So one group of replicas is going to have all of the data for a particular username, but each username might have a different set of replicas. The second item there, the follower, is what we call a clustering key. So Cassandra, this is a really important part of Cassandra and how you model your data. It stores the data in a particular order, and you really want to take advantage of that ordering. So in this case, we don't care about the order of the followers too much. The next example will show that, but in this case, it's all of the followers. Basically, all of that data is going to be stored contiguously on disk for a single username. So that means that when we go to read all of the followers for a single user, Cassandra can basically just do one contiguous sequential read on disk and return the results. So that's just a couple milliseconds. It's very fast. Yeah, that's what you want. You want to optimize for reads. So say we want to track all of the tweets by a user. This table it's similar to the previous one. Just got the username, a tweet ID, which is a time UUID. So the Python class UUID, I don't know if y'all have played with it, gets used a lot in Cassandra. The one that's most useful is a version 1 UUID, which we just call a time UUID. Basically, it's a timestamp with a bunch of random components. So it's a way to kind of have a timestamp and guarantee uniqueness, so you don't have to worry about conflicts. So we can safely use username and tweet ID for our primary key and not worry about having 2 identical tweet IDs and those overlapping. But the nice thing is that since tweet ID is in that clustering key position, it's going to be sorted by time. So on disk, all of the tweets by a user will be sorted by time and stored in that order contiguously on disk. And this last bit at the end, the with clustering order by, normally it sorts them in ascending order. All I'm doing there is changing it to be descending order so we can get the most recent events first. So then you can just do queries like this. If you just want to get the most recent 100 tweets by a user, you do that. Again, it's one sequential read on disk for Cassandra. It's extremely fast, a couple of milliseconds, even on a cold read, and you're done. So tweets by follow, it gets a little more interesting. Say you wanted, this is for supporting the query, basically show me the last 100 tweets by anybody I'm following. This is similar to the table we just looked at before. Almost identical, in fact. Again, it's keyed by the username. We've got that tweet ID, which is a time UUID, so it's ordered by time again. Then we've got the author of the actual text, or the tweet, the body of the tweet, and it's stored in time, sorted order, descending again. So this shows a particular pattern that tends to be different in Cassandra and relational databases. So normally what you want to do in a case like this in Cassandra is actually denormalize. You want to write this tweet out to, whenever you make a tweet, you want to append it to every follower's timeline. So that tends to scare people who come from a relational background because you want to normalize, you want to only write once, and you don't want to keep writing this duplicate data everywhere. But with Cassandra, writes are extremely cheap. And Cassandra is really based around the idea that disk space is cheap. And if you can use extra disk space to save almost any other resource, it's a good trade-off. So in this case, we're making that trade-off. We're using potentially 100 times more disk space, say if you have 100 followers, but the increase in read efficiency is huge. It lets you always do these sequential reads, and that's really going to save you a ton of I/O. Now, this pattern might fall down in some cases. If you've got Justin Bieber with like 10 million followers, however many it is, I have no idea. You might want to, this pattern might not be the best case for those high-end users, right? You don't want to, every time he tweets, you have to write out 10 million rows. That might take it a little too far. So you do have to be conscious of what the pen out looks like. But for most cases, denormalizing is the better option. You always want to try and optimize your reads. Cool. I didn't know it would do that, but that's pretty much it. If you want to see the full example website, there's actually one running at Twissandra.com. Thankfully, the spam bots have like filled it up with ads for shoes, but it's still running. It's still running. And you can see a little bit more how it's actually used in Django there. You'll notice that it's not interacting with the ORM at all. It's all kind of hand-coded methods, but it'll just show you how you'd actually use the driver to query these data models. It's showing a few of the kind of usage patterns I talked about, where you're maybe doing asynchronous queries and building up a list of futures and then reading all those futures at once. So I'm going to be cleaning up a little bit over the next few days probably, but it's even right now it's still probably useful to look at if you're interested. So that's it for me. Did anybody have questions about like Twissandra or where this data model might have problems? Or yeah.
Yeah. So you define a schema there with your ordering and everything. What happens if you decide I don't want to order anymore by in reverse order? I want to order in ascending order.
Then you copy all your data to a second table.
Okay.
So, yeah. Cassandra, you can manipulate your schema in some ways. It's really easy. And in other ways, it's difficult. So you can add columns for free. It's not like MySQL. if you add a column, basically, it's kind of like all columns are optional. There's no way to enforce not null or anything like that. It's kind of like all columns are optional. So when you add a new column, it doesn't try and backfill the old data. It just, whenever it reads that row, it sees that the column's not there, and it just sort of assigns that column a null value. So it's easy to add columns. Deleting columns is also cheap, but it doesn't clean up all of the data immediately. It kind of slowly works it out of the system over time. But yeah, you can't change the clustering order. You can't change the partition key, right? Because that would require shuffling all of the data around the cluster again. So in some ways it's flexible, in some ways it's not. There are a couple of cool kind of things that are flexible in the schema that I didn't mention. One is collections. You can define a column to be a collection, either a list, a set, or a map. So if you have something where, say, you're doing like a playlist of songs, and you want to have tags for the songs, you might use a set column there. You definitely don't want to do columns like tag 1, tag 2, tag 3. That's not a good idea. Just use a set there. So that can give you a little bit of flexibility, and you're still working with typed data. So there are a few options there. We also have user-defined types coming up, which are kind of like C structs, I think. You can just kind of mash several fields into one type, and that's a user-defined type. So it can support kind of a document style, or it can support document style data relatively well. Yes?
So taking your Twitter example a little farther, if
Sure.
you wanted to tweet out like a picture,
Yeah.
would you store that picture in Cassandra or some other data store and just have it into it?
Sure. So Cassandra can store blobs. It can store large blobs, but it's not necessarily the best choice for that. What we usually see users do is they'll store the metadata in Cassandra, and they'll store the actual image with something else that's more designed for that kind of storage. So if it is something really small, like a few K, I think, or even up to single-digit megs, Cassandra will do reasonably well with that. The problem is kind of with these really large column values. Whenever Cassandra pulls that into memory, that kind of creates some problems for garbage collection. It also kind of slows it down with a few other maintenance operations. So like I said, Cassandra can do it pretty well. If you want to store bigger objects, you can break them up, but that's not what it was optimized for. So there are other storage systems that will do a better job. Anything else? Cool. All right, I'm going to go ahead and turn it over to Joaquin. In that case, then. Yeah. Sorry, I don't actually use them.
That's the very last one.
Full screen. All right. Thanks, guys.
Yes. So, is this on? So
You just gotta talk like right into it.
Hello.
Yeah.
My name's Joaquin. I typically stutter, especially on my name, so you could bear with me. That'd be awesome. But yeah, so I started picking up Django, I guess in October. I did a little bit of work in it till about November, and recently been picking it back up. So yeah, just to show you a little bit of Django sessions now then with the new Python driver that I've been helping to QA as Tyler writes out. So yeah, I guess I talked about most of that. But yeah, so right now I've gone through and I've updated the Django sessions. I wanted to go ahead and have users and messages done by today. but like everything that never happens, right? Hopefully soon I'll be able to take a look at the authentication piece and check to see if that would also work well for translating that into, or being able to use that with Cassandra. So yeah, on the bottom is the link to the GitHub repo. It is in the update to CQL tree because I went ahead and sent that back to a repo that's been dead for about 3 years. So hopefully they accept it and update it. Yeah. So going over a little bit of the high pieces. I went through, created a key space called Django Cassandra. For this case, I went and set a replication factor of 1, just because most times we're probably just testing it out, and you'll probably only have 1 node. And then for the primary key, I just went ahead and set the session key up for that. And then the session data, it's a map of blobs. So yeah, so this is the main init piece. I tried to make it large enough for it to be seen in the back. But essentially, you go through, you create a cluster object once and a session object once. You keep that, and that's going to be used throughout. So for my Django side project, I pretty much have just 1 file. I create that, I hold on to it, and I use that all the way through. Because we're pretty much using a lot of loads and deletes, I'm just going to go ahead and prepare those once. I'll set the consistency levels once to quorum on both sides. That way, if I have a replication factor of 3, I make sure that I'm going to write to at least 2 nodes, and when I read back, it'll be 2 nodes. So we get strong consistency, and we're able to lose a node and still keep going. Yeah, and then at the end I catch it. Make sure that if for whatever reason that schema isn't there, don't go through. Don't create it dynamically. Even though you probably could. It's just better to go through and manually handle that yourself. So yeah, my helper method, it takes a prepared statement. And the bind tuples. For the inserts, because we are using TTLs, I'm going to go ahead and re-prepare that if it turns out that the last time it changed. What's up?
You want to explain TTLs?
Oh yeah, sorry. So TTLs are times, or it's short for time to live. So if you're pretty much going through and storing a session data object, and you want it to live for the next hour, those TTLs will be set, and Cassandra will honor them. So if time passes and you're now at the 2-hour mark and you try to read it, it will still be there on disk, and stays around for the system to make sure that it propagates that delete fine. But as far as any crimes are concerned, that data will not be coming back out. So let's see. Yeah, so the next part is the save part. I did go ahead and implement this. If must create is true, it checks to see if it does exist. You're not actually supposed to do that with Cassandra, just because reads before writes are costly. And generally, what you're trying to do is structure everything toward you writing once and then you reading on totally separate operation. But in this case, we did it because the specs said that we had to. So yeah, and then for exists, we go through again. We send in the prepared statement. We send in our bind variables. If the result is an empty array, then nothing existed. If there was something in it, then it will return that in the first value. Yeah, and then just kind of highlighting that with the TTLs, we will be able to go through and churn those out without having to do any sort of manual operation on the system. Yeah, so a little bit of what I learned through that was just kind of to be able to keep my views, my library, database, and Cassandra totally separate. I went ahead and redid everything as soon as I got to a really good point, which I was totally happy with. And I know you're not supposed to do a version 2 as soon as you complete a version 1 or rewrite everything, but I did, and it worked incredibly well. With that database layer, I pretty much had my sessions and all of my prepared statements. So when I changed my entire schema up, I was able to see exactly what needed to be changed, and I didn't have to mess with any library portions or reviews as much. Yeah, and Tyler really doesn't like them, but I love them. So if you end up using the dictionary factory, what you end up getting is a nice little session key kind of, or an array of all your columns. If not, then it will give you the name tuples that Tyler talked about earlier. Right now I do have a pull request out on the Python drivers, so that way you'd be able to do things like send in your bound statement and send in a dictionary of your bound or your binding values. It does need a test case and to be cleaned up just a little bit. I'm working with it right now, and it seems good. In SQL 2.0, it will actually, in the next Python driver, it's going to be part of the language, right? Is that correct? Yeah. So, and then here's a little bit of my side project and me actually going through and handling some financial data. Typically, financial data wants to be on relational databases just because that's the way they've been for a very long time. But here I went ahead and showed that with the primary key, the date and the transaction ID, I go ahead and hold on to that. So that way I'm able to ensure that every time something gets written, it's going to be a new date, so that's going to be a new row. And it's always going to be appended, so I have a full history. And then the transaction ID is really what I'm going to be looking at, and just kind of making sure that this is unique and this transaction is worth this much money. And again, I go through, I prepare it. I could go ahead and set certain things like status to open, so that way all future executions of this query will have that. And then save history, I go ahead and pull out the prepared statement and send it back in. I will probably go ahead and change that to match closer with what I recently did with the Django sessions. I just haven't had time. And if you wanted to get started with Cassandra today, I do have the Cassandra launcher project. You pretty much go through, you do a pip install, you run it once, and it's going to move the cluster launcher config out of user etc local or whatever, and it's going to toss that into your home directory. Go through, give it to your AWS keys, and it will go through launch cluster for you. So if you want a simple one node in EC2, let me show you that. It does go through, it raises all your ephemeral disks. It makes sure that all the system settings are correct. It installs it dynamically, so you get the very newest version. It installs Off Center for you, and that's all a separate project, also written in Python. And if you end up deciding that you want to go into production today and you need 10 nodes, you run the same script. It gives you 10 nodes, they're all run together, and you hit the ground running. So are there any questions over all the stuff that I just said? Cool. So thank you very much again for coming, and thank you very much for having both of us, and we'll be around for a little bit if you all have any more questions. Thanks.